Midterms in Automata Theory and Formal Languages.
Hi everyone! Hi Prof. Doka Lagos. Now, I'm going to present about how to convert decimal to binary and decimal to octal, decimal to hexadecimal. Presented by me, Herby G. Estrella, BSCS 3 New Mod, First Year, Second Term, 2023-2024. Now, let's discuss about decimal to binary conversion. It is converting a decimal to binary involves repeatedly dividing the decimal number by 2 and noting the remainders. The binary equivalent is obtained by reading the remainders in reverse order. The computation method is start with decimal number, keep dividing by 2, and write down the remainders reverse. Let's start with the whole number example. Decimal number 26. First is divide repeatedly by 2 until it becomes 0. When 26 is divided by 2, the quotient is 13 and the remainder is 0. When 13 is divided by 2, the quotient is 6 and the remainder is 1. When 6 divided by 2, the quotient is 3 and the remainder is 0. When 3 is divided by 2, the quotient is 1 and the remainder is 1. When 1 is divided by 2, the quotient is 0 and the remainder is 1. And now write down the remainders in reverse. Therefore, the binary equivalent of the decimal number 26 is 11010 or 26 base 10 equals to 11010 base 2. Next is the fraction example. Decimal number 26.5. The process involves handling the whole number and fractional parts separately and combining them for the final binary representation. With the answer earlier, the whole number 11010. Let's compute the fractional part. First is get the 0.5 to the 26.5. First is multiply the fractional part repeatedly by 2 until it becomes 0. When 0.5 is multiplied by 2, the result is 10.5. When 10.5 is multiplied by 2, the result is 1.0. Then after that, no decimal part remains. So we reverse that into 0.1. Then adding the fractional part to the whole number, binary representation, 11010 to 0.1 equals to 11010.1. Therefore, the binary equivalent of the decimal number 26.5 is 11010.1 or 26.5 in base 10 equals to 11010.1 in base 2. Next is decimal to octal conversion. It is converting a decimal number to octal involves repeatedly dividing the decimal number by 8 and noting the remainders. The octal equivalent is obtained by reading the remainders in reverse order. The computation method is start with decimal number, keep dividing by 8, write down the remainders reverse. Now let's give an example with a whole number. Decimal number 135. Divide repeatedly by 8 until it becomes 0. When 135 is divided by 8, the quotient is 16 and the remainder is 7. When 16 is divided by 8, the quotient is 2 and the remainder is 0. When 2 is divided by 8, the quotient is 0 and the remainder is 2. And now write down the remainders in reverse, resulting to 207. Therefore, the octal equivalent of the decimal number 135 is 207 or 135 in base 10 is equal to 207 in base 8. Now, for the fraction example, decimal number 135.5, the process involves handling the whole number and the fractional part separately, combining them for the final octal representation. With the whole number solved earlier, the whole number is 207. Let's separate the 135.5 with its decimal, which is 0.5. And 0.5 is multiplied by 8, the result is 4.0. And next is no decimal part remains, which if we write down in reverse, the fraction is 0.4. Now adding the fractional part to the whole number, octal representation, 207 plus 0.4 equals to 207.4. Then the octal equivalent of the decimal number 135.5 is 207.4 or 135.5 in base 10 equals to 207.4 in base 8. Next is the decimal to hexadecimal conversion. It is converting a decimal number to hexadecimal involves repeatedly dividing the decimal number by 16 and noting the remainders. The hexadecimal equivalent is obtained by reading the remainders in reverse order and using letters A to F for remainders 10 to 15. The computation method is start with the decimal number, keep dividing by 16. Check if the remainder is 10 to 15, which is equals to A to F. First is, let's get an example with a whole number. Decimal number 255. Divide repeatedly by 16 until it becomes 0. When 255 is divided by 16, the quotient is 15, and the remainder is 15. When 15 is divided by 16, the quotient is 0, and the remainder is 15. The two remainder is 15. So let's convert the remainder 15 in hexadecimal, which is equivalent to F. So FF. Therefore, the hexadecimal equivalent of the decimal number 255 is FF, or 255 in base 10 is equals to FF in base 16. And let's get a fraction example. Decimal number 255.5. The process involves handling the whole number and the fractional parts separately and combining them for the final hexadecimal representation, which we solved earlier. The 255 with the two remainders 15 is equals to FF. Now let's solve its fractional part, 0.5. When 0.5 is multiplied by 16, the result is 8.0. And next is no decimal part remains, which the final fraction is in reverse 0.8. Then add the fractional part to the whole number hexadecimal representation. FF plus 0.8 is equals to FF.8. Therefore, the whole equivalent of the decimal number 255.5 is equals to FF.8, or 255.5 in base 10 is equals to FF.8 in base 16. Next is the importance of number system conversions. This proficiency is foundational for professionals and students alike, contributing significantly to the advancement of technology and efficient problem solving. First is digital electronics. Engineers and technicians working with digital circuits need to interpret and manipulate binary, octal, and hexadecimal representations to design and troubleshoot electronic systems effectively. Second is computer programming. Proficiency in number system conversions is essential for writing efficient algorithms, optimizing code, and debugging programs. Third is networking and communication. Network administrators and engineers need this knowledge to configure and troubleshoot network devices and ensure seamless communication. Fourth is cryptography and security. Encryption algorithms often use binary and hexadecimal representations to manipulate and secure data. Fifth is data storage and compression. Similarly, compression algorithms may utilize various number systems to reduce files while preserving essential information. Thank you for listening. Please comment down below what are your more questions submitted to Prof. Doc Alagos. Thank you for watching.